Okay, so I'm going to start by putting up our syllabus here, and you can see that today we're going to talk about a little bit of review of how to compose two functions, and then we're going to talk about the chain rule, which is the rule you use to take the derivative of the composition of two functions. So we'll spend 2 days on the chain rule. It's a really, really important one. So, you know, really work hard today and Wednesday to make this make sense to you, because it will haunt you the rest of the semester. Okay, it will just keep coming up. So today I'm assigning two projects, steel drum and pipeline. So steel drum is about building a steel drum, a 55-gallon steel drum, like the kind that the oil is shipped in. It actually has to hold 57 gallons because you have to allow for some expansion and contraction of the liquid inside the barrel. So it has to have a volume of 57 gallons. And we want to build this thing, this 55-gallon drum, for minimum costs, right? So that word minimum should be like calculus, calculus, right? So we're trying to build a 55-gallon steel drum for minimum costs. I have given you a little timeline here and some diagrams. This is how the steel drum is built. It's not a complicated object. We take one rectangular sheet of steel, curl it up to make the barrel part, the cylindrical part, and then you put a disc on the top and a disc on the bottom and like crimp them together. And I've given you a bunch of costs, how much the steel costs, how much it costs to weld steel, how much it costs to seal the top to the cylinder. And the rest of the project walks you through little bit by little bit how to do this problem. Yes? We are. We are, yeah, in question 5. So 1 through 4 is about calculating your cost function. And then in question 5, yeah, most mathematicians would just ignore the volume lost, but we're treating this problem a bit more like an engineer than a mathematician. What? I actually told you at the end of the project. So here it is in number 5. We say, unfortunately, the volume of the drum isn't simply pi r squared h because some of the metal is lost in the crimping together process. And because we take this lid and we set it down into the barrel a little bit. So you lose a little bit of height, you lose a little bit of radius. So we are going to take into account the volume lost in the construction process. And then the very last part of this project is I tell you the American National Standards specification diagram. This is actually how a steel drum is built. And you want to compare your results that minimize cost to the American National Standard. If you want a spoiler, they do not come out the same. Yeah. And there are a couple places in here where I tell you what you should get, so you can kind of know if you're on the right track as you go along. Crimping is not the right word. I don't really know. It's called a pressing/sealing machine that for the top, to make the top attached to the cylinder part and the bottom. Okay, so brief discussion of pipeline project. Similarly, I've given you an outline of what days you should be doing which exercises to try to keep you on a steady pace to be done by the due date. So a common problem encountered by the oil industry is determining the most cost-effective pipeline route in connecting various wells in an oil-fertile area, right? So here's a well, we need to lay some pipe between them. What's the most cost-effective way to do it? So on the back of the page is a section of a U.S. geographical contour map of Northeast Ohio with some wetlands outlined for clarity. Okay. Well, you don't have to, it just costs more money to lay your pipe through the wetlands than it does on dry ground. So, I mean, the fastest, most straight route, right, would be to just connect your two oil wells, right? But it costs a lot of money to have your pipe go through wetlands. So that is going to be an expensive option. You could go all the way around, right? That's one option. You could go around the other way. That's another option. You could like go part way down the wetlands and then cross so that you spend the least time possible in the wetlands. Or maybe it's better if we cross at some magical point, right, that we don't know where it is. Right? Straight down from A and then over. Yep, that might be a good option. Right, yeah. So it's hard to tell exactly what the best method is until I tell you exactly how much it costs to go through the wetlands versus the dry land. And we need to sort of analyze this thing with some calculus to minimize the cost, again, minimizing cost. So the problems in this project will walk you through how to set up a formula for the cost and figure out what the minimum cost is. So first, like somebody said, I was hoping we weren't going to be accounting for the volume lost. You said that, right? So sort of a typical mathematician's approach is to make this thing simpler, right? So that we might first start out by saying, let's pretend that this wetlands is a perfect rectangle, right? So that's what we do here. So first you're going to draw a rectangle and get something like this. Okay. Say this might be a rectangle. We've got A and B, and we got to find the most economical way around the wetlands. But it's not a rectangle, right? So then you'll move on, and then maybe we'll treat the wetlands like a trapezoid. A trapezoid is a pretty decent approximation of those wetlands. And then we're going to just sort of do the same problem again, but now we're using a trapezoid, and we want to find the most economical route. So that's the deal with the pipeline problem. So those are due on, steel drum is due on October 27th, pipeline is due on October 29th. Those dates are in your syllabus. Any questions? Okay. Okay, so we've got a new packet today, jumping into the second third of the course, third of the way through. So this first page is a reference sheet. You can bring it to the test. You can use it on your take-home quiz. And it just has formulas for different kinds of functions. So we know the first two right now, and that's it. Right? We're going to learn a whole bunch. We're going to learn a whole bunch more before the next test. Different kinds of functions we can take the derivative of. Then we also have some general formulas for more complex functions. We know this one, and this one, and this one, and this one. Right? We know how to take the derivative of a sum or difference and a product and a quotient by using the product rule and the quotient rule. And today we're going to start learning the chain rule. So this is a general strategy guide for differentiation. This is something, again, a reference sheet that you can refer to as we learn more and more formulas. You can always come back and look at this as a reference. Okay, so composition review and the chain rule, day number 1. So today we're going to learn a new derivative rule called the chain rule. It is used to take the derivative of composite functions. So we're also going to briefly review composite functions. We will do this look over your test on Wednesday. Third and fourth projects are assigned today, doing about 3 weeks. Like with the last projects, I really strongly encourage you to talk to each other. We do have a project check-in day partway through, about halfway to the due date, that you'll have class time to do that as well. Stay on schedule. Don't wait until the last minute. Yep. Okay. So let's begin with a review of composition of functions. So we're going to let f of x be the square root of x and g of x be 3x plus 1. We want to evaluate f of g of x. So who remembers? Yeah, can you explain what you're doing, how you did that?
Yeah, you do it as the value of g of x, then substitute that value for the
Yeah. So the f function is typically f of x, right? And whatever's in parentheses means the input into f. So now I'm inputting g of x into f. So I could write this as the square root of g of x, right? And then replace g of x with its formula. So this is the square root of 3x plus 1. So hopefully this is a review, something that feels comfortable to you. Exactly as if I had written f of smiley face, right, would be the square root of smiley face. If I write f of g of x, that means the square root of g of x. And then you can replace g of x with its formula. Okay, so now I have h of x is the quantity x squared minus x plus 1, all raised to the 23rd power. So let's find two functions f and g so that when you compose them, when you plug g into f, you get this result h. Sure, f of x could be x to the 23rd. And g of x would be the inner function, x squared minus x plus 1. Yeah, like decomposing, yeah. Does that make sense? So if I were to have taken this formula for g of x and replace it with use it to replace the x in the f formula, I would get h of x. Okay, so that's just a little review of composition of functions. We're now going to present a new derivative rule that allows us to take the derivative of composite functions, the chain rule. So I've written it down in 3 different versions here. The English one, to me, feels the easiest to work with, but you might find a different one easiest to work with. So it says, to take the derivative of a composition, take the derivative of the outside function, evaluate it at the inside function, then multiply by the derivative of the inside function. Version 2, this is a mixed notation because I'm using primes and ddx's. So this says if you want to take d dx of f of g of x, that's the derivative of a composite function. You take f prime of g of x, so you take the derivative of the outer function, the f, evaluate it at the inner function g, then times the derivative of the inner function, g prime. That is d dx of f of some stuff is f prime of that stuff times the derivative of the stuff. And then in Leibniz notation, you introduce a new variable and you say y is a function of z and z is a function of x. So this is like y of z of x. That's your composition. So dy dx is dy dz times dz dx. And we call it the chain rule because this looks like a chain linked by the dz's. So at this point in the semester, we don't have a good justification for why the chain rule works, so we just got to take it on faith for now. We'll just learn how to use it. Later on, we'll learn why it works. Okay, so let's find the derivatives of these 2 compositions that we talked about at the very start of class. So I want to take the derivative of y equals the square root of 3x plus 1. So how have we been rewriting square root to make it easier to take the derivative? 1/2 power. So I'm going to do that first. 3x plus 1 the 1/2. All right, so if I want to take y prime, this is some stuff to a power. So apply the power rule to the stuff first. So what would I write if I was going to apply the power rule here? There we go. So I applied the power rule. And if that were all I had to do, the chain rule would be easy, right? But so I've got my power rule applied to the stuff. So I've taken the derivative of the stuff. Then you also have to multiply by the derivative of the inside function. What is the inside function in this case? 3x plus 1, so its derivative is 3. So actually, maybe I'll write times d dx of 3x plus 1. So this ends up being y prime is equal to 1/2 times 3x plus 1 to the negative 1/2 times 3. Yeah. You could simplify it to 3/2. Yeah. I don't care. Oh, so the book would write this as, if we were going to simplify this, yeah, we'd have 3 on top over 2 times the square root of 3x plus 1. Because that's to the negative 1/2, which means it would belong in the denominator. And you rewrite it as a square root. In general, so in this case, my rule of thumb says I should have simplified this. So my rule of thumb is if you can simplify it in like 1 or 2 moves, you should do it. Otherwise, just leave it. So this one I would have simplified. But the simplification isn't the really important part. I want to emphasize the chain rule. Why is that being so crazy? Yeah, I did. Okay, so let's look at the next one. I've got some stuff to the 23rd power. Apply the power rule to the stuff. So I'm going to bring down the 23, copy what's inside, just like you do when you do the regular chain rule. You bring down the power, copy the x, reduce the exponent by 1, so that's going to be the 22. Then multiply times the derivative of the inside, which is what? 2x minus 1. And in this case, I would not simplify it. Okay, so a really super common mistake I will warn you about now is that people try to do this, combine these 2 steps into one, and they would go like this. Right? So they try to combine taking the derivative of the outside and the inside into one step. So they bring down the 23, they reduce the power by 22, and then instead of rewriting the inside function here, they do the derivative of the inside step at the wrong time, right? So this is wrong. Right? Just be careful. It's a 2-step process. Derivative of the outside times the derivative of the inside. Yeah, you have to be able to recognize it as a composite function. If you were given which function? Yeah, you recognize that as a composite.
Well, I mean, like not just given to like what just like the power rule, it's not.
If it was just x to the 23rd, it is 2 functions combined together. I don't know what you mean. So if it was just x to the 23rd, right, if I wanted to take the derivative of that, the chain rule still kind of applies to our old power rule, right? I bring the 23 down, I copy the x, I reduce the exponent by 1, and then I multiply by the derivative of the inside function. But the inside function is just an x, right? And what's the derivative of x? 1. So the chain rule like still applies when it's not a composition of functions. It's just the derivative of the inside is 1. So it always applies. All right, you do some.